resultant vectors. You may have a couple of vectors, like this one. I'm going to put the little cross at the beginning. This one that I might name vector x. Yeah, it's going to be a little bit glitchy. Do you want me to restart?
Yeah.
As long as you say what you're doing.
Yeah, you know what? I'm not going to restart. We'll just deal with the glitchiness. Vector x. And we might have vector y. And we all know that if we add up vector x plus vector y, we could express it algebraically. And last time we talked about it, we talked about this vector system adding up to vector z or something like that. I'd like to switch it up a little bit. Instead of saying vector z for the total, I want to call it vector r for resultant. We could just as easily say vector capital T for total or something like that. But just for argument's sake, we'll use r for resultant, okay? X plus vector y plus vector z gives us a resultant. So if I had vector x plus vector y, and I drew it graphically, it might look something like this. Vx plus vy, and we had a specific way that we talked about adding vectors one after another. It was a t to t rule. What was it? T to t. Tip to tail, yeah, tip to tail. And if we add two vectors tip to tail, we always get a resultant which starts from the beginning of the one vector and goes to the end of the other vector. And a resultant is the sum of two vectors, but really more broadly it's the sum of two or more vectors. Because you can have more than two vectors added tip to tail. We've got two vectors here, but we could have more. And so we could also define, as a reference frame, north, south, east, and west. And we could define positive and negative directions as well. Last day, we assigned specific values to this x component and y component. Yes, sir?
Okay, so the vector resultant, is that always going to connect the two?
Yeah.
Okay.
It's really kind of like saying, hey, this resultant vector is the sum or the result of what happened with all the other vectors kind of getting added up tip to tail.
Okay.
Okay? Almost like saying it's equivalent to them all getting added up. Okay? So by definition, if I have something that's pointing in the x direction and something that's pointing in the y direction, what angle is between those two vectors?
A right angle.
Beautiful. I like the way you think. A beautiful mind. X and y at right angles to each other, okay? If I happen to know the y component and the x component, I'm putting check marks there to indicate that I know them, and I wanted to know the magnitude of the resultant vector, could I do it? What's that fancy theorem that we said could do that? Yeah? I love it. VR is equal to the square root of Vx squared plus Vy squared. And that's just that Pythagorean theorem. Nothing fancy. Well, it is fancy, but nothing new. Okay? Let's say I knew this x and this y component and I wanted to know the angle, because as we all know, a vector needs a direction. What's the trig ratio if I know this side and this side to get this angle? Now, if this is the angle we're talking about, this side is what? Opposite or adjacent? Opposite. This one is adjacent. And if we didn't know the hypotenuse yet, I would probably try to use these two initial given values, if I was given them, to figure out the theta. So what's the trig ratio I should use? Tan. Beautiful. So of the choices, SO, CA, and TOA, I would use tan, or the TOA. Tan of theta equals, in this case, opposite is Vy, and the adjacent is Vx. Okay? And so, of course, I could get tan inverse. Okay? No problem. So let's say we did all that. And let's say, because this is a pretend, okay? But let's pretend we did all that. We were given a Vx and a Vy, and somehow we came out with the value that this resultant vector was 50.0 meters per second. You know, v is for vector, but v is also for velocity. 50.0 meters per second. And let's say that we knew our Vx and our Vy and we figured out that the angle was 23 degrees. 23.0 degrees even. Yeah?
It's tan -1, right?
Oh, thank you so much. Tan -1. Let's say that we found the angle to be 23 degrees.
I think that's it.
Thank you. That would mean that I have a vector, like this one here, that points off 50 meters per second at an angle of 23 degrees. And if somebody wanted to indicate the true vector, resultant vector, that is v with the arrow over top, resultant vector, resultant velocity, I'd write 50.0 meters per second. And then how would I indicate the direction? Starting off obviously with a square bracket, but then what would I do? Yeah? I like it. East, 23.0 degrees north. Now there's an alternate way that we could write it that I brought up previously. It started off with the 23 degrees. 23 degrees, do you remember it? Yeah, north of the east. And we just write north of east. So that's an equally valid way to write it, and you'll see both ways from time to time. What if I had a vector that looked like this? Now, this is a what if. What if I had a vector that looked like this? Okay, you don't have to write this, so don't distract yourself with writing it down. I want you just to focus on figuring it out. I got an angle of, you know what? Let's make this not to scale. Let's make this 60 degrees. And let's say that the magnitude, let's make it a displacement vector this time. The magnitude of this displacement vector was 506 meters. How could I write that down? Magnitude, units, direction. If I had just figured this out for a word problem, for example. Yes, sir?
West 60 degrees north.
West 60 degrees north. No. No. I like the way you're thinking. You're going more or less in the right direction. Yes, ma'am?
North 60 degrees west?
Yeah, I could say 506 meters. Point yourself north. Rotate yourself 60 degrees to the west. Now that wouldn't even be the best answer, because what we've said previously is that 60 degrees is greater than 45, and really and truly, a lot of the textbook answers, and a lot of people that care about such things, choose the smaller value than 45 degrees. So if it's 60 degrees, what makes up the 90 degrees? What angle would be required to make up the remainder of the 90 degrees? Yes, sir?
30.
Yeah, 30. This is an easy one. I chose an easy number so that we could do it quickly. The way I'd get that is 90 minus 60 equals 30, and I know that's what you did in your head. But if it was something like, not 60 degrees, but 72.96, you'd have to take 90 minus 72.96, and whatever was left over, that would be the angle that we're really concerned about. But this is a pretty easy one, nice round values. So I'd say west 30 degrees north. Now north 30 degrees west, or 60 degrees west, and west 30 degrees north, those guys are equivalent, but that's preferred, the smaller of the two. Everybody sort of got that? Okay.